Nikari, and I am going to explain you on the topic what is Bloom filter and how we count distinct element in a stream by using an example application of crawling the web. The web task uses different processes so as to crawl the pages. How we filter content in a stream. The crawler maintains the list of URL it has already seen. Each URL on the list will be assigned some task whose job is to look at page and report back the link if it finds. But we don't want some same URL on the link twice, because then we would waste time crawling the same page twice. Every time the URL comes to the central control, it has to report whether the URL has been seen before and discard the same URL. So we can create, say, hash table to look up the URL which has already been seen, but the web is very big, so the index here will not fit in the main memory. What is the role of Bloom filter? When URL arrives on the stream by crawling task, we can pass it through Bloom filter. This filter will say either the filter has seen before or not. If the filter says that it has not seen before, then the URL will be added to the list of URL to be crawled and eventually be added to some crawling task. But in some cases, the Bloom filter may be false positive, say either the URL has been seen before. In fact, it is not. If the Bloom filter say the URL has never been seen before, then there is no false negative. How a Bloom filter works. A filter is an array of bits as possible of several elements in a stream. The bit array is manipulated using hash function, which could be a good choice in some situation as it returns a position in the array. Initially, all bits are 0. When input x arrives in the bit of h of x, where h is represented in binary for each hash function h. So I am going to explain you through an example. Here is a tiny example which uses 11 bits to filter an element, which consists of two hash functions, h1 of x, which is computed from integer x. We will write x in binary through an odd position, counting them from right. Position 1 is low ordered, position 3 is 4th order, position 5 is 16, and so on. Suppose integer is I, then compute I modulo 11, which is when I is divided by 11. h2 of x is computed in same way but from the even position of binary representation of x. So here what happens when 3 integer arrives? Initially the 11 representation of Bloom filter is 0. The first integer is 25. We show the value in binary with odd number position and even number position. h1 is formed from odd position, which is 1, 0, 1. That is 5 in binary, and 5 modulo 11 is 5. Even position is 10, that is 2, and 2 modulo 11 is 2. So we therefore set position 2 and 5 to the value 1. The next integer to arrive is 159, which is written in binary as well. The odd positions are 0, 1, 1, 1, which is 7, and even position forms are 1, 0, 1, 1, which is 11 in decimal, and 11 modulo 11 is 0. So here 7 and 0 are two hash functions, and which we have to change in the filter content to 1. The next value to arrive here is 585. Here the odd positions are 0, 1, 0, 0, 1, which is 9 in decimal, and 9 modulo 11 is 9. Even positions are 1, 0, 1, 0, which is 18, and modulo 11 is 7. So here we set 9 and 7 to 1. Here already 7 is already changed to 1 in the filter content. What is Bloom filter lookup? Suppose element y appears in the stream and we want to know whether the URL has already been seen before. So we will compute the value of h of y, where y is a representation in binary, by using an hash function y. If all the resulting bit positions are 1, then we will we will conclude that the y has already been seen before then, and as it could be a false positive. If at least one of these positions is 0, say, then we would say that the y has not seen before, as it could be false negative. What is the application of Bloom filter? Here is a sample application for this problem. We might be crawling websites. We want to know how many different spam sites have been created in order to know whether it has been created by spammers or not. When the spammer has to create a great number of pages, then he might use copies of same page over and over. One would expect the total sites, or they could take the random page from the web where the site have no convergence topic. When the number of distinct words is unexpectedly large, then the major websites like to advertise how many features of the sites or could have been on the most recent day remark. Suppose we are crawling the web page we used to afford to follow from link, the job would never end. So we have to cut the search at some point, as we don't know what link exists in that page and which page could be crawled and which page need not to be crawled. So like we are so here like Facebook, where the number of users are increasing day by day, so the spammer could create a false link in it. So the approximation of attacks on the users could be more or high depending on the crawls he used.
My name is Prakar Pradhan, and I'm going to continue on our topic of counting distinct elements in a stream. So, if in a given problem, if our data stream consisting of elements chosen from a set of size n, and if we have to maintain a count of the number of distinct elements seen so far, what would we do? The obvious approach to solve such a problem is to keep in a memory a list of all the elements seen so far in the stream, keeping them in an efficient search structure such as hash table or search tree, so one can quickly add new elements and check whether or not the elements that just arrived on the stream was already seen. So the problem in doing such a method would be if the number of distinct elements is too great, or if there are too many streams that need to be processed at once, then we cannot store the needed data in the main memory. Now there are several options like using more machines, each machine handling only one or several of the streams, or store it in a secondary memory. Or we could use the algorithms to only estimate the number of distinct elements but use much less memory than that of the distinct elements. One such approach would be the Flageolet-Martin approach. It is possible to estimate the number of distinct elements by hashing the elements of the universal set to a bit string that is sufficiently long. The length of the bit string must be sufficient that there are more possible results of hash functions than there are elements of the universal sets. 64 bits is sufficient to hash URLs. The idea behind the Flageolet-Martin approach algorithm is the more different elements we see in the stream, the more different hash values we shall see. As we see more different hash values, it becomes more likely that one of the values will be unusual. When we apply a hash function h to a stream element a, the bit string h of a will end in some number of zeros, possibly none. For each stream element a, let a be the number of trailings in h. R will be the maximum number of a seen. Estimating 2 of R for the number of distinct elements seen in the stream. So basically how it works is the probability that a given stream element A has h of A endings in at least R zeros is 2 to the power minus R. If there are m distinct elements, the probability that none of them has tail length at least R is 1 minus 2 to the power minus I whole to the power m. The equation can be rewritten as 1 minus 2 to the power minus R, the whole to the power 2 to the power R, the whole to the power m into 2 to the power minus R. If R is reasonably large, the linear expression is of the form 1 minus e to the power 1 by e, which is equals to 1 by e. The probability of not finding a stream with as many as R zeros at the end of its hash values is e to the power minus m into 2 to the power minus R. Thus we can say that if m is much larger than 2 to the power r, then the probability that we shall find a tail length at least r approaches 1. and vice versa. If m is much less than 2 to the power r, then the probability of finding a tail length at least r approaches 0. The problem to such a algorithm is, considering a value r such that 2 to the power r is much larger than m, there is some probability p that r is the largest number of zeros at the end of hash values. The probability of finding r plus 1 to be the largest number of zeros is p by 2. If we increase by 1, the number of zeros at the end of hash values, the value 2 to the power r doubles. For each possible large r, to the expected value of 2 to the power r grows as r grows. So the expected value of 2 to the power is actually infinite. The other algorithm would be combining estimates. It is another way of combining the estimates. Take the median of all the estimates. The median is not affected by the occasional outsized value of r. So the problem of 2 to the power r becoming infinite is actually solved. But the problem in such a proposed algorithm is it is always to the power of 2. So no matter how many hash functions we use, should the correct value of m be between two powers of 2, it is possible to obtain a close estimate. So the problem to both the problems would be, we have to combine both the methods, that is the flageolet Martin algorithm and the combining estimates. We have to firstly group the hash functions into small groups, then take the average, then take the median of all the averages. Occasional outsized 2 to the power r will bias some of the group and make them too large. In order to guarantee that any possible average can be obtained, the groups should be sized at least a small multiple of log base 2m. Space requirements. In a red stream, it is not necessary to store the elements seen. The only thing required in the main memory is one integer per hash function. This integer records the largest tail length seen so far for that hash function and any stream element. So the space requirements problem is basically solved. The conclusion would be, with the help of these two algorithms, we can compute the number of distinct elements in a stream in a reasonable amount of main memory. Thank you.